In the last video, we talked about solids and liquids, so I'll kind of finish up and talk about gases. I'm just going to draw the graph of R and potential energy again. Alright, and we're just saying that the lowest potential energy is at this equilibrium point. You can remember that we said solids were kind of separated by about R equilibrium distance apart. And liquids were maybe a little bit further than R equilibrium. And then gases were much farther. Okay, so when we think about gases, they're really just these atoms and molecules that are just kind of flying around, okay? They kind of go where they please, they're going really fast. There are no restrictions on their movements. Now in a liquid, remember, they were kind of constrained and couldn't really go necessarily wherever they wanted to go. And that's because they were close enough together that there were still those attractive forces between them, and they kind of kept them together. And that's kind of like if you don't expect the like water in your glass to kind of just like spread out over your room, right? They all have to stick together. And that's because they're close enough together that those attractive forces are keeping them together. Gases, if you sprayed a thing of perfume, you wouldn't expect all the perfume gas to kind of stay together. You would spread across the room. And the thing I'm getting at here is that the potential energy of gas must be equal to 0. Right? They are not stable. They're not unstable. It's not like they're all going to go in a particular place, right? But in our soccer analogy, this would just be like a ball that's kind of just resting on normal ground. The gas molecules or atoms, they can kind of go wherever they want without a please. Okay? And so they really just don't need to worry about how they relate to the other gas molecules, right? So go wherever they please. And this also shows us why gases kind of don't keep their shape or keep their volume, right? Solids were kind of locked into this structure, so they kept their shape. Liquids were allowed to, like, the molecules had to stay close together. They could flow by each other, but they would take the shape of their container. And gases, like liquids, will kind of just take the shape of their container, but they will actually fill the container, right? The gas molecules are likely to spread out, filling their container. And unlike solids and liquids, which can't be compressed, liquids can be. Because the molecules are so far apart, we could push them together. And they could be pushed together and be much closer, but still not be near that equilibrium distance, or that repulsive force won't start getting to them, right? So gas can actually, when liquid becomes gas, there's something around like a 1700 times change in volume, right? The molecules are way more spread out in a gas than a liquid. And that just shows you that they're just really far apart. And that's why they're so far apart that you can actually push them back together. And if you think about this as springs, they won't get close enough for that kind of repulsive force as though there were a spring there. Another thing to remind you guys, if solids are around here on the graph, say liquids are around here, right? So they're both pretty stable. Solids especially stable because they have that crystalline structure. Well, gases must be around here if they have 0 potential energy. And you can also see that if I wanted to get from a solid to a liquid to a gas, I would have to add energy, right? This is potential energy. I'm in the negative. So to climb out of the negative, I would have to add energy to get to 0, or maybe just a little less negative. So to put numbers on this, say a solid had negative 10 units of negative potential energy, and liquid had maybe negative 8, and a gas had 0.